So this title of the talk is Colossal Black Hole Eruptions. This is one of my interest areas in scientific research. And what you see on the picture is an example of a colossal black hole eruption. There's a galaxy right down here at the center. And these streamers coming out of the center of the galaxy were propelled out by energetic events happening near the black hole. So we're going to get to black holes. But a lot of this talk is going to be motivated by some of the general questions that astronomers try to solve, like what's out there, how did it get there, and how did we human beings get here? If nothing else, we won't find answers to all those questions today, but you might also just enjoy the pictures, because this particular talk has some of the most beautiful pictures that I know of in astronomy. So first, I want to talk a little bit about what a galaxy is like. Now, our Milky Way is a galaxy, and you might have seen on a dark night, if you know where to look, a band of light across the sky. This is a beautiful picture of the Milky Way in the sky taken from Hawaii. I actually have a version of this picture above the fireplace in the family room. And it shows these stars, the 100 million or more stars, sorry, 100 billion or more stars that are in the Milky Way. And you also see patches, dark patches that are gas clouds. And in this direction, this is the center of our galaxy. And I'm going to be showing you evidence in a little bit of the black hole that lives right down in the center of our galaxy. Here's more of an astronomer's view of the Milky Way. This is actually a picture of the whole sky. It was made up of many smaller pictures that were stitched together to make something like a world map, except instead of taking the skin off a globe and trying to flatten it out like this world map over here, this picture is taking pictures in all directions of the sky and stitching them together to make a map of the entire sky. So if we superimpose all the constellations on this, you might recognize some of these constellations. Ursa Major up here is the Big Dipper. Over here is the constellation Orion. In the center, there's constellations like Sagittarius and Scorpius. And the center of our galaxy is most closely associated with the constellation Sagittarius. Okay, so in this picture, you can see anywhere. And if you want to know whether you're looking at the center of the galaxy, if you can find the constellation Sagittarius, you can look at that. Another point I want to make about this picture is we're not seeing everywhere in the galaxy. These dark regions are where gas clouds in our galaxy are hiding our view. And so if you want to know what's behind them, we need to look in regions of the spectrum that are not visible. One good one is infrared light, because infrared light goes through these gas clouds more easily than visible light. When we make a map of the sky using infrared pictures, it looks more like this, okay? And so you can see there's still some dark gas clouds visible, but now you can see more clearly the bulge of our galaxy at the center, how thin the disk of our galaxy is. These are two satellite galaxies that orbit the Milky Way. They're the Large and Small Magellanic Clouds. And so with infrared light, we're more easily seeing through the galaxy to see what it's like. And its basic structure is that there's a bulge at the center. It's about 27,000 light years away from the sun. There's this thin disk, maybe 1,000 light years thick. Side to side, it's about 100,000 light years across, the visible part of the disk. And it looks like it does in the sky because we're in the disk and we're seeing this whole thing edge on. If we could step off to the side, our galaxy would look more like this picture. This is actually a picture of the nearest spiral galaxy to our own, the big spiral galaxy in the constellation Andromeda, showing the bulge, the disk. The halo is a spherical region around the whole thing. The disk bulge kind of live within the halo. These dark clouds are sometimes called the interstellar medium, which is another way of saying the gas between the stars. And we've come to appreciate that in addition to these components of a galaxy, every large galaxy that we've been able to take a close enough look at also has a very massive black hole in its center. So you might be wondering, how do we know there's a black hole at the center of our own galaxy? I am now going to take you on a picture journey from the Milky Way seen on largest scales all the way down to the center in order to acquaint you with the evidence for the black hole that's there. So here again is our all-sky map of the Milky Way. And I'm going to have you focus on the center. And I'm going to put a little picture there. And I'm going to blow that one up. So we're looking at just this little square at the center. We're going to make it bigger. And now you're seeing that this kind of diffuse glow is many, many, many stars. You can't even pick them out individually. If we're looking at the center of that, here's some dark gas clouds that are mostly obscuring our view. This is invisible light, but if we use infrared cameras, we can look closer to the center. I'm going to blow that one up. And here is a more intimate view of the center. Now we're looking at a region that's only maybe 1,000 light years across the whole image. The center of the galaxy is here. Even at infrared light, there's still gas clouds that the light doesn't penetrate. This glowing red stuff is glowing gas. And in addition to infrared light, sometimes we can learn also about deep within our galaxy by using radio telescopes to measure the radio waves that are coming from our galaxy. When we look at the same region with radio telescopes, it looks something like this, okay? So right near the center, there's intense radio glow. There are some kind of balls that correspond to explosions of stars that happened in the past. There are also filaments, these narrow, bright streaks that are energetic particles that are trapped on magnetic field lines near the galaxy, but something had to energize those particles, and we'll be talking about the black hole in that context in a little bit. I'm gonna get rid of the radio image for a second, and we're gonna take another piece and zoom in further. This is now a composite image made up of observations from 3 different NASA observatories. There's the Chandra X-ray Observatory. X-rays have an easier time passing through the galaxy. So this is an X-ray picture of the center. There is the Hubble Space Telescope picture of infrared light. And there's also the Spitzer Space Telescope, which looks at longer wavelength infrared light and tells us more about the gases that are there. There are some, one of the most massive stars in the galaxy is over here, the Pistol Star. But Sagittarius A, this region is where the black hole is. You can see filaments of gas out here labeled arched filaments. And when we look in radio waves at the same region, we see that these filaments that were evident in the radio picture are connected with the gaseous filaments, but also connect back towards this region where we think the black hole is. So let's zoom in further. Right now, just to acquaint you, this is a 50 light year scale bar, so we're seeing a smaller region. We're going to now narrow down to this region around Sagittarius A star. This is now the another infrared light picture from the Hubble Space Telescope, and now we're getting in pretty tight. The scale bar now shows 5 light years at the center. If we look in radio light, we see there's swirling gas. We can still see it swirling around the center. And we can try to zoom in even further. Maybe blow this region up, okay? So in this part of the galaxy, we're now looking down at a region that's only a little more than a light year across. To give you some perspective, the next nearest star other than the sun, or the nearest star to the sun, you could say, is about 4 light years away. So in our neighborhood of the galaxy, there would only be a couple stars in this picture, but in this region of the Milky Way, right down at the center, there's a whole lot more, thousands of stars. But we're going to zoom in even further. We're going to zoom into this region. And what this image shows, in addition to the bright blobs of light, which are the stars, there are also some lines, elliptical lines, showing the orbits of stars. And so now we're looking at such a small region of space that over the course of a couple decades, we can observe the stars moving. Okay, this work was done at UCLA, at the Galactic Center group there. It's taken a lot of patience to get this set of observations that map out how the stars are moving. And I want to zoom in even further on that. So here is the central region. And what I want to draw your attention to in particular, I'm going to start a movie. I want you to be looking at star S02, or sorry, SO2, star SO16. It really doesn't look rainbow colored. Those colors now are just trying to represent different amounts of intensity in the star's light. The star is really not that color, but that's the nature of this observation. So I want you to look at what those stars do with respect to this white star at the center. There's nothing, as you'll see the stars move, you will see no light coming from the point marked by the white star. That's where the black hole is. And I'll just run the movie so you can see what all the fuss is about. So 1995, the stars were here. And now we're starting to march through the years and watch. You can see stars make a quick turn around that region where the white star is, marked by the white star. In fact, all these stars you can see in the picture are orbiting around that one spot. I'll let the movie go again. Remember, watch S016 here, and it makes a quick turn. Next star makes a quick turn. These stars are responding to the force of gravity, and by the way those stars are turning right at that spot, you can tell there's got to be something with a lot of gravity there, but we can't see it, okay? And we can measure the mass by the orbits of the stars. There's about 4 million times the mass of the sun right at that spot. And the only thing we know of that can be so massive and so invisible is a black hole, something that if you get close enough, not even light can escape it. I do see a question about the talk being recorded. And yes, the talk is being recorded. And you can contact Corey if you want to get a copy or another viewing of the talk. So we're making that available. Now, what would a black hole look like if you could get very close? If you did see the movie Interstellar, you would have seen them represent the black hole like this. This inside the circle here, it's dark. Light can't escape the black hole itself, so there's no light coming from it. But if there's stuff nearby, particularly stuff orbiting in a disk, and so this is representing the disk, there's stuff orbiting in front in this disk, and that stuff is energized and can glow. But then there's this light over the top and this light around the bottom. You might wonder, what is that supposed to represent? In physical space, this is a black hole surrounded by a flat disk with a hole in the middle. But light from the back side ordinarily would not come in our direction. But because the gravity of the black hole is so strong, light from the back side is getting pulled over top of the black hole and ends up hitting our direction. So you're actually seeing the other side of the disk because the light from it has been bent over top of the black hole. And light from the bottom of the disk on the other side is getting bent and is coming around the black hole in the other direction. So if you see a movie like Interstellar and someone says, this is what a black hole looks like, that's what you're actually seeing. You're not seeing the black hole itself. You're seeing the glow from gas as close to it as gas can possibly get without falling in. And the black hole's gravity is bending the light paths, so our view of it is highly distorted. If you're wondering how scientifically realistic that is, one of the consultants for this movie was a guy named Kip Thorne. I got to meet him when I was a postdoc at Caltech, and he was a professor. He also won the Nobel Prize in Physics a couple years ago for his work in black holes and general relativity. So they had Nobel Prize winner working on this visualization. So it's about as accurate as they can make it. I now want you to take you on a journey to see another black hole. It's in a galaxy known as M87. It's an even bigger galaxy than the Milky Way. And it is one of the biggest galaxies in our part of the universe. And its black hole has a mass that's 6 billion times the mass of the sun. It's about 2,000 times more massive than the one we just talked about. And so we're going to zoom in on that one. And there's some music that goes with this video that was put together. So there's 100,000 light years across. This is a visible light picture. And we're going to zoom in further. You can see some X-rays from this object. As we get closer, you're going to see a Hubble Space Telescope picture, and I want to draw your attention to the streak that is an eruption from the black hole. As we zoom in further, most of the data is going to start coming from radio telescopes that can give us the most precise views that we can possibly have of objects out in space. We're now down within a few hundred light years, down to less than a light year. And as we continue to zoom in, we see that this eruption is coming from a very localized region at the center. And in a couple more zooms, we will see a very remarkable picture. It's the first ever image of the space around a black hole. You might remember the press release about it 2 years ago. And it's from a collaboration called the Event Horizon Telescope, which is not just one telescope, but it's a whole network of telescopes all over the planet that were used in combination to map out the light from the very center. And when I say light, I mean radio waves, from the very center of the galaxy M87. What you can see in the image is there's a shadow at the center and a blurry glow around it. This is somewhat like that image you saw that was made for Interstellar. That one was made on a computer. What calculations say the region around a black hole would look like. A few years later, with radio telescopes, this image was made. You might complain it's a little blurry, but in fact, it's by far the most precise image we've ever been able to make of something out in space. And it shows the region around this black hole. We can measure where the black hole is by where it's dark. And the labels on here are comparing the size of this black hole to the solar system. So at the center is the sun. Neptune's orbit is this circle here. And this black hole, if it were where the sun is, we would be inside of it. Also labeled here are Voyager 2 and Voyager 1. They are the two things made by humans that we've been able to send as far as possible. They were launched in the 1970s. They're still traveling away. They're several times further out than Neptune and maybe just as far across as the black hole. So this gives you some sense of this black hole, but to see it required an enormous effort. I would not be surprised if the Event Horizon Telescope team wins a Nobel Prize for doing this sometime in the next decade. So now I want to turn to the concept of eruptions. Here is now an artist's conception of what a black hole eruption might look like if you were right there next to the black hole. What you see is a disk of gas that's swirling around the black hole, and it's falling in. As that gas falls in, it releases a whole lot of energy. You might be familiar with gravitational potential energy from your time in school. As something falls, it releases gravitational potential energy. The matter falls into the black hole, but the release of energy can propel other things outward from the vicinity of the black hole. So this bluish stuff is stuff that's caught on magnetic field lines and getting propelled outwards from the center. And that is an artist's conception of how you might get an eruption from the center of a galaxy driven by a black hole. So what I want to turn to now is what the consequences are of one of these eruptions for the rest of the galaxy. So I'll go back to this picture showing the Andromeda Galaxy, where you can see where the stars are. You can see where some of the gas is. But if we zoom out, we now have a lot of evidence that the galaxy doesn't stop at the edge of where the stars are. In fact, there's lots of gas surrounding the galaxy itself. How do we know? When we look at some very distant light sources behind the galaxy, their light passes through this region, not going through the galaxy, and it leaves signals behind in the light we observe that tells us about the gas that surrounds the galaxy. That goes by the name of the circumgalactic medium, and it has a lot to do with how galaxies form and how they change over time and how they sustain star formation. So I now take you back to the picture that started the talk. What you're seeing here is a massive galaxy. It's more like this galaxy M87 than it's like the Milky Way. The yellow and white are its visible light. And this pink and red is actually a radio wave image. So the evidence for the eruption around this galaxy is coming from radio waves. So what we can tell without seeing the gas around the galaxy directly is there's an eruption, but it's also running into something. The stream doesn't just keep going. It seems to be running into something like a fire hose running into a wall, and then some of that stuff is collecting. But if you have an X-ray telescope that's sensitive to seeing hot gas, you can see what's actually out there. And that's what we use the Chandra X-ray Observatory for. Now the pink stuff is turned blue in this composite image. And the purple glow is the X-ray light from around the galaxy. And it's telling us that around this galaxy where the stars are down here, there's a lot more gas that's at temperatures of millions of degrees. The eruption is tunneling through it, and there's even more gas out here that's ramming up against. And so in trying to understand what black holes are doing, how they get there, how they influence the galaxy around them, our group at Michigan State combines observations of the Hubble Space Telescope and observations from the Chandra X-ray Observatory to look at these eruptions and try to understand how they're influencing the history of a galaxy. I'm now going to show you, well, we also do computer simulations. This next movie is from a supercomputer simulation of how a black hole eruption interacts with hot gas around a galaxy. And the color is indicating the temperature of the gas. So the fact that this is orange right now indicates it's a temperature of a few times 10 to the 7 degrees. That's 30 million degrees roughly, 30, 40 million degrees. When I start the movie, you will see some of it change its temperature, okay? So I'll start the movie going. There's now an eruption coming out in 2 directions. And you can see around the galaxy now, there's colder gas that's developed along the eruptions, and it's spread over a region that's hundreds of thousands of light years in size, so bigger across than the Milky Way galaxy. What this reminds me of as a scientist is what happens in a thunderstorm, one of which took down my cherry tree yesterday, right over here. We had bad thunderstorms here in the Lansing area, took out my cherry tree. But what happens in a thunderstorm is you get updrafts of air. That air is hot and humid. As it rises, it cools. And as it cools, it starts to form, the water starts to condense out and starts to rain back down. Something similar is going on here. As the eruption happens, there's hot stuff that's welling upward, but it's pulling up other gas behind it in its wake. And as that gas gets pulled up, it cools and starts to form clouds that fall back into the galaxy. Why do we think this is happening? Well, we can model it in a supercomputer simulation, and we can also use the Hubble Space Telescope we'll let it fall back down there. We can also use the Hubble Space Telescope to look at galaxies like this. These are now images in ultraviolet light with the Hubble Space Telescope over regions that are hundreds of thousands of light years in size. And we see gas that's been pulled up along the eruption, and it's forming stars. The ultraviolet glow is from new star formation, showing us that when these eruptions happen, they can also be related to the formation of stars within the galaxy that are associated with this upwelling of gas and kind of rain of gas back down into the center. So I will now play a longer movie of an even larger region of space, made another supercomputer simulation. My collaborator who did this thought it might be nice to set this to the music of Mozart, so I'll just let that play. There's been an eruption in this collection of gas at the center, but as that runs out, more gas cools and makes a new eruption. And if you watch this movie for a while, you can see this interplay between eruptions and cooling is actually regulating all the gas around the galaxy. It's going to run out of cold gas in a bit. And then a new eruption cycle will start over. So that's pretty. I love watching that movie. I love listening to the music. But it also helps to illustrate how we go about doing this research. If you look over here at the time signal, this 6.53 GYR means 6.53 gigayears. In other words, on the computer, what we've just simulated is 6 billion years of time. We're looking at a very significant part of the history of the universe. And we need to do that in astronomy because we don't have time to watch all this happen. What we can do is do computer models, applying laws of physics to what we see out in space, to see how events unfold over very long periods of time. And by doing that, we can test those models then by taking snapshots of what we see and trying to relate the two, okay? And so at Michigan State, I have two collaborators who work with me very closely in this. One is my wife, Megan Donahue, who does the observational side, and my colleague Brian O'Shea is an expert in numerical simulations. And I guess I'm the puzzle solver. I try to figure it out. But it's been a very fruitful collaboration. Okay, so now I want to comment on why did the eruptions matter? I did promise to say something about how we got here. And now I want to play another simulation for you. It's actually from another group, but I like showing it because they did a great job with the visualization. This is known as the Illustrious simulation. And I'll describe what you're seeing as it unfolds because the different colors that you're seeing, what they're representing will change over the course of the simulation. So let's start it up. The foreground will be rotating from left to right, right? So I don't want you to get sick watching this. I want to orient you. Space isn't actually spinning like this. They're rotating the camera around so you can get a sense of how things are distributed in space. This counter here is telling you how far from the Big Bang you are. Right now we're 1.4 billion years. And right now what you're looking at is dark matter collecting. It's stuff you can't see with a telescope. There's a lot of it out there. Its gravity pulls matter into clumps. The gas follows. And as gas cools, where it's been collected by dark matter, it starts to form stars. So the next color map is going to be gas temperature, where red is hot and blue is cold. That's what you're looking at now. You can see that the regions where most of the matter has collected are the reddest and the hottest. You also see that they're tending to flicker and flash because in this simulation, it's accounted for the black hole eruptions. And you can see that the black hole eruptions are having a quite dramatic effect on the gas around the galaxy. Also, what's happening there is there's a lot of star formation. The stars are making the elements that are necessary for life: oxygen, iron, they all come, silicon, sulfur, calcium. They're all made in stars. They get distributed out into space when those stars explode. And the black hole eruptions are the most powerful things of all that stir this matter. And so now what you're seeing in the color map, green's representing regions that are enriched in these new elements, purple are regions that are not as enriched in elements. And you can see how the elements are now spread through space as galaxies are trying to develop more and more stars, more and more planets, and perhaps life. So the black hole eruptions are part of that cycle, and we're still trying to figure out the details of that, okay? I have a question here. What do I mean by enriched and not as rich new elements? What I'm doing is I'm comparing the amount of, let's just say, oxygen. If you measure how many oxygen atoms for each hydrogen atom we have out there, that's telling you the amount that that gas has been, had elements put into it by new star formation. In the Big Bang starts with mostly hydrogen gas with some helium gas. If that's all you have, then you're not going to be very successful at forming planets or human beings. You have to form things like oxygen, silicon, sulfur, iron, etc., calcium. And so you have to wait for stars to form, for stars to explode, to put those elements out there in space. Then they have to be recycled. Gravity in the interstellar space needs to pull gas clouds together. And this recycling process eventually is the basis for our solar system formation. So what I mean by enriched is the making of things that are not just hydrogen and helium. I also have a question that says, are the explosions shown and lustrous? Are they galaxy size or galaxy cluster size or larger? That's very much on target to my area of research. I would say they can be galaxy size or bigger, but they don't quite get bigger than a galaxy cluster. I will be turning a paper into the Astrophysical Journal this week that's actually commenting on that issue. So that question is quite appropriate. I will now, now you might be asking yourself, does the Milky Way's black hole do this? I'll take you back to our all-sky image, and I'll show you one more piece of evidence. If this is an all-sky view of what visible light looks like, there's another NASA satellite known as the Fermi satellite, named after Nobel Prize-winning physicist Enrico Fermi, that is looking for gamma rays, the most energetic kinds of light there is. And if we look at the whole sky in gamma rays, what we see is this, okay? So if you look closely, you see the Milky Way has bubbles of its own that are, most of us who work on this subject think they represent an eruption from the Milky Way's black hole that's not currently erupting. This may have happened several million years ago. And if the Milky Way is like the other galaxies we see around us, we do think that eruptions like this happen occasionally. Just how often? I have another question here. It says, how frequent are black hole eruptions? Again, I'd love, yeah, that's the kind of thing I work on. In the center of a galaxy cluster, they seem to be happening almost all the time. Around galaxies that are less massive, like the Milky Way, maybe only 10% of the time or 1% of the time. We're still trying to figure out what that relationship is. The Milky Way's black hole right now is unusually quiet. It's even more quiet than we would expect a black hole like that to be. And that what was so exciting about finding these bubbles was it was the first, I think, the first clear evidence that the Milky Way's central black hole has not always been as quiet as it is today. And there was an email question somebody asked before the talk, could you address the correlation of Fermi bubbles and black hole activity at Sagittarius A star? That question indicated someone's done a lot of reading on this issue, because these things here are the Fermi bubbles, and Sagittarius A star is a radio astronomer's way of saying the place where the black hole is. So this relationship between the Fermi bubbles and the black hole is one of the big pieces of evidence that black hole eruptions have occurred in the Milky Way galaxy, where they have probably played a role in helping distribute the elements that are made by stars as this galactic recycling process has gone on through the last 14 billion years, 13 billion years, one of the results of which is human life. So I will bring the talk to a close there, and I will start taking your questions. I see one here. It says, what, if anything, does the pattern of motions around the black hole let us know about the internal structure of the black hole inside the event horizon? Is it possible, theoretically or in practice, to map how mass is arranged inside the black hole and how the mass is rotating or moving? Okay, so the first answer to that question is the pattern of motions of the stars. Looking at the orbits of stars, they can tell us about the mass of the black hole, maybe a little bit about rotation, but they really don't get close enough to probe more than that. So the way we hope to learn more in the future about the black hole and its properties is through observations of gravitational waves. Some of you might have heard of the Laser Interferometry Gravitational Observatory, or LIGO. That is technically what Kip Thorne won the Nobel Prize for, his role in developing that observatory. And they have detected a few mergers of black hole with another black hole over the past several years. That is the best way of learning about what black holes are like. It is not, the question was, can we map how mass is arranged inside the black hole? Once things are inside the black hole, we can't learn much more about them, but we can measure things like how much is the black hole spinning? Or how are the black holes, how is the space around the black holes deformed during the process of merging? I think we're in the early days of that part of science. There are more observatories like LIGO coming online. The US had the first two. Europe has one. India has one. Other countries are building them. And the more observatories we have of this kind, the better we're going to be able to do learning about what black holes are like, especially when two black holes merge with each other. I have another question here. When you say the Milky Way black hole is quiet right now, when is now? Right, astronomers are always facing this question, what do you mean by now? When I give a talk in person, sometimes I remind the audience, I'm not seeing you all out there as you are right now. I'm seeing you as you were a nanosecond ago or 10 nanoseconds ago, because it takes light time to travel. The center of our galaxy is about 27,000 light years away. That means whatever's happening there now, those light signals won't get here for another 27,000 years. But when I'm talking about this particular sense of the word now, when looking at the region around the black hole, it appears it hasn't been disturbed by a black hole eruption probably for well over 100,000 years. So that is the sense in which I mean now. It's very much an astronomer's use of the word when now is the last 100,000 years or so. Someone asks, does galaxy size or density affect how often the central black hole will erupt? Boy, these are astute questions. This paper that I'm going to send off to the Astrophysical Journal is actually discussing the question of how the size and density of a galaxy affect the black hole. In the movie, you saw the movie I showed with the Mozart music was showing a simulation where the black hole was regulating the cooling of gas around it. And so we think this feedback loop that the black hole participates in manages how rapidly a galaxy can form its gas into stars. And so when a galaxy gets big enough, this process seems to limit the amount of stars can form. But observationally, there seems to be direct evidence that there is a relationship between the galaxy size and density and how often it will erupt. So the answer, as the question is phrased, is yes, it definitely does. If I could give you more precise answers right now, I would. But this is the very kind of edge of scientific research at the moment in this area. I have another question. The sun rotates around the center of our galaxy, the black hole. Does the center of the Milky Way rotate around anything? How fast is the galaxy center moving? And what is it moving from, to, around, in relation to? Okay, so I'll orient you. We're in the disk of the galaxies. The sun is, and all the stars nearby it are orbiting around the Milky Way center. That orbit takes about 200 million years. So last time we were on this side of the galaxy, dinosaurs were just getting started on Earth. And we've made maybe 50 or 70 orbits around the center of our galaxy. So then the question is, well, what does the Milky Way go around? The Milky Way is part of what we call the local group. So I showed you a picture of the Andromeda galaxy. It is the other big galaxy in our local group of galaxies. In that all-sky picture of the Milky Way, there are those large and small Magellanic Clouds. They orbit around the Milky Way itself. They're not very massive. And to some extent, the Milky Way and the Andromeda galaxy orbit, but it's not a circular orbit. It's an orbit that will take them into collision about 5 billion years from now. So the Milky Way isn't going around something in a circle. It's kind of moving out, now back. And if I were giving you another talk about collisions between galaxies, I would have shown you a movie of the collision, the predicted collision between the Milky Way galaxy and the Andromeda galaxy. And if you want to see that collision happen live, you're going to have to live for another 5 billion years. Another question. Are the energy ejections from the black hole, the energy from the spiraling gas as it heats up from acceleration before it falls inside the event horizon? I have heard before that black holes evaporate over eons of time. Are the ejections related to that? Okay. So the answer to the first question is basically yes. As the spiraling gas goes in, it's releasing a lot of energy. It's heating up some, it's starting to move very quickly. And so a lot more falls in that gets flung out, but in that trade-off, if you release a lot of energy by throwing some gas into a black hole, and just a little bit of it is, some of that energy is given to some of the gas that didn't fall in, the gas that didn't fall in can be coming out at very high speeds. So, so that's how that process is thought to work. It is true also, or at least it's theoretically predicted by Stephen Hawking, that black holes evaporate over eons of time. And the key word there is eons. It takes enormous amounts of time for a black hole like the one of our center of a galaxy to evaporate, like 10 to the 100 power years. Okay, and so while in principle, there's energy that can come out through that process, the ejections that I'm talking about, the eruptions I'm talking about, are not associated with the evaporation part. Okay, another question. Do we know what the rotational periods of black holes are? Well, only in a very limited sense. A black hole by itself, right now, well, yeah, we can, yeah. We have no way of really measuring its rotation, a black hole by itself. The only exceptions are when we measure the gravitational wave pulse of a black hole merger. And so what's happening there is as the black holes get very close, they start emitting these waves called gravitational waves. Energy comes out and the black holes start spiraling closer together. As they get closer and closer, the orbit is down to a fraction of a second. And the pulses that we're measuring, the gravitational waves that we're measuring, are actually telling us what the orbital period is of those black holes around each other right up until the very end. So normally the answer to the question, do we know what the rotational black holes, periods of black holes are, is no. But in the few cases where mergers have been detected, we are actually measuring those orbital periods over a very limited amount of time. Okay. Next question. In the first movie, I understand the star's slingshot trajectory, but I don't understand the path of the star that appeared to bounce off the black hole. Well, that is just, the appearance of a bounce is the star going very close to the black hole around the other side and coming out the other direction. If you've ever seen the trajectory of a comet on a map, comets come in almost straight into the sun, then go around the far side and come back out. That's like the orbit of the star you saw appear to bounce, but it really ran around the far side of the black hole, and then, you know, the gravity kind of whipped it around and it went out. So that's why you had the appearance of the bounce. Next question. When the black hole erupts and affects the gas that is in the halo, and can we see this gas because of its heat compared to the background radiation? Well, around a very massive galaxy, the gas is so hot that it emits detectable X-rays. That's a large part of what our group at Michigan State does, is try to observe the X-rays from the halo so we can study these eruptions. As you start looking at smaller and smaller galaxies, that gets harder to do. It isn't as hot, the gas isn't as hot, it doesn't emit as much radiation. We're trying to push the envelope on that. Being able to distinguish it from other possible background forms of radiation gets harder and harder. But if we're gonna learn about it, we have to push the envelope there. And we're trying to figure out clever ways to do it. Okay. I got a question. Do you believe the universe began from one black hole, the Big Bang? In a way, yeah. The interesting word there is believe. You know, sometimes my students, when I'm teaching, especially the class for non-majors, they ask me questions like, do you believe in aliens? Do you believe in the Big Bang? And I try to shift that to say, let's talk about what the evidence is. And so when we try to understand how the universe got started, and we look at the evidence we've been able to collect really strongly supports the Big Bang theory of how the universe got started. That theory can't say anything about the very first moment, like why did it happen at all. It is a theory for if the universe started in a very hot state, where matter was really closely packed together, and then it expanded from there and gravity started to form galaxies, etc. We have a very successful picture of what we're seeing. Lots and lots of evidence supports it. But I hope you get my nuance. I want to have a conversation about what does the evidence support or not support, rather than what I believe. Another question. When stars go around a black hole, do they always go in the same orbit, or is it random? Okay, so the way these stars are orbiting the black hole at the center of our galaxy, it's not like how stars orbit or how planets orbit the sun. If we look at our solar system, everything's going in the same direction and really in the same plane. We're talking about orbits around the black hole at the center. Those orbits tend to be more elongated or elliptical. They can also be oriented in different planes, okay? But they aren't random they are still they still are going periodically around the black hole. If you just looked at one of them, it would look organized. If you look at all the different orbits, they don't look as organized, but I wouldn't call it random. They may be on random orientations, but the orbits themselves are quite organized. Okay. Another question. When a black hole merger occurs, do the eruptions increase proportionally by the size of the two original black holes? What these eruptions depend on most is how much gas is falling in. It depends less on the total mass of the black hole. The amount of gas that can fall in at once is dependent on the mass of the black hole, but the eruption itself depends mostly on how much stuff you dump in. So the reason the Milky Way isn't erupting at the moment is right now there's no gas being dumped on the central black hole. And usually the bigger something is, the bigger an eruption it can have. And so that remains true with black holes. Yeah, the black hole merger by itself doesn't increase the size of the eruptions. You also have to dump something onto the black hole. Okay. Next question. What tool are you most looking forward to being built, which will help you answer your questions? What information are you looking for in your research? Wow. It depends how selfish I'm being. Right now, the astronomy community is doing its once a decade homework to try to figure out what new instruments look like the most promising things. There are 4 telescopes, large ones, under investigation by NASA. I'm most interested in 2 of them that can tell us something about the gas around galaxies, so we can learn more about this whole environment the galaxies are in. One of them is the successor to the Hubble Space Telescope that have a much bigger mirror and collect a lot more light. The other is, and that one is called LUVOIR. The other is LYNX, which is the next generation X-ray observatory that can help us map out the hot gases around galaxies.